The continuum provides the modeling substrate for this system, a persistent, overlapping background where every local structure emerges from fluid energy patterns. Watch the sudden eruption of activity surging from those waves. It looks like a solid, formidable structure. Human intuition often mistakes this kind of peak intensity for structural permanence. We assume a bright signal is a reliable anchor. A spike without a validated state representation is mathematically inadmissible. If the model treats a transient burst as a fixed anchor, any subsequent claims about the system's stability will lose coherence the moment the burst fades. Within the UHS framework, appearance is a poor metric for stability. A core must earn its status through a proven durability threshold. Separating a fleeting illusion from a structural anchor requires a rigorous, three-stage mathematical audit. The audit begins by freezing the dynamic activity at the surface. We need to examine the static topography supporting these spikes. This topographical grid reveals the difference. While the energy spikes look identical, the underlying geometry is not. One sits over a shallow dip, the other rests in a deep, narrow basin. The shallow dip flattens under pressure. Its spike quickly dissolves because the geometry cannot physically contain the energy. The deep basin proves the energy is geometrically localized. It provides a structural home, allowing the spike to pass the localization check. Geometric localization is a mandatory prerequisite, but a structure requires more than a deep basin to survive a hostile environment. The perturbation stress test acts as a health monitor. It strikes the localized structure to see if it can survive an active hit. We apply bounded perturbations, small, mathematically defined environmental disturbances that strike the basin. This first waveform shatters immediately upon impact. Because it cannot recover its position, it is rejected as unstable. This second subject survives low noise, rocking back and forth, but as the frequency of the pulses increases, it violently ejects from its basin. This is metastable behavior. The model flags metastable cores with a warning. Their conditional persistence makes them unreliable anchors for long-term downstream networks. This third waveform absorbs the hits. It dampens the incoming energy and reliably returns to the center of the basin. The model evaluates persistence as a continuous variable. It measures how effectively a structure dampens a strike and returns to its resting state. The final trial tests the surviving stable core in a multi-core environment. It must prove it can function alongside others. Dropping a second stable core nearby creates overlapping stress zones, where the radiating influence of both structures interacts. This heat map highlights conflict zones. Overlapping vibrations cancel each other out, destabilizing both cores. But in coexistent safe regions, phase relations align, creating a harmonious pattern that reinforces both centers. A core can only graduate to building larger networks once it proves it can coexist with its neighbors without causing structural contradictions. After surviving the topography check, the stress test, and the multi-core load, the candidate is officially certified. All of the core's physical history is now compressed into a compact parameter tuple, a data bundle summarizing its stability class and coupling readiness. This data bundle is a non-negotiable contract required before the model allows the system to scale up. This tuple is the blueprint used to radiate fields, construct protective shells, and connect bridges to the rest of the lattice. Resilience and recovery define stability. The audit ensures that before a system scales, its foundational anchors can survive the friction of the continuum.